Another important rule for how we find antiderivatives or indefinite integrals is the linearity rule. This works the same as the linearity rule that you learned for derivatives. I'm not sure if you remember that it was called the linearity rule, but hopefully this will look at least a little bit familiar. So if we suppose that f and g are two functions and that a and b are two constants, then if we're trying to integrate a times f of x plus b times g of x, that result is just going to be a times the integral of f of x plus b times the integral of g of x. What that means basically is that we can pull the constants outside the integrals, and we can also separately find the antiderivatives of two functions that are being added or subtracted together. This may look a little bit simpler through the example than through its definition. So let's do these examples. So let's suppose we want to find the integral of 3x squared plus 5x dx. Well, what I can do is using this rule where the constants are, that's a and that's b, and this is f and this is g. So x squared and x are the two functions, 3 and 5 are the two constants. What I can do is I can rewrite this as 3 times the integral of x squared dx plus 5 times the integral of x dx, like that. So we now know how to find these antiderivatives. That's just going to be 3 times, this is going to be x cubed over 3 is the antiderivative of x squared, and then plus 5 times x squared over 2. And don't worry, I'll add in the plus c at the end. This is just going to be x cubed plus 5 halves x squared plus c. Now, by the way, you might wonder, why didn't I have to add in, let's say, a plus c there? The answer is I could have, but if you look at what I would have gotten is oops, that disappeared. What I would have gotten is 3 times plus c here. Let's actually write this out. Let's suppose that I had just written this as 3 times x cubed over 3 plus c plus 5 times x squared over 2. And I need a new name for the constant because it would be a different constant, so I'll just call it d. What I would end up with is x cubed over 3 plus 5 halves x squared plus 3c plus 5d. But take a look at this. All this is representing is the idea that I could pick two arbitrary real numbers, multiply them by 3 and 5 respectively, and get some other real number. In other words, this expression represents every possible real number that can exist. And since the whole point of the plus c is just to be able to say that we can add any constant to the main part of the derivative, there's no reason to write it in this overly complicated form. So since it's always going to come out that way, what I can do at the end is simply write the plus c at the end after finding the main parts of the derivative, as I've done here. Okay, let's do a slightly more complicated example. Let's do the integral of square root of x squared plus 3 over x dx, like that. So this doesn't look like it's in the correct form because we don't yet have any sort of way of dealing with product functions, but fortunately this is a pretty easy function to distribute, so we can just rewrite it this way. Square root of x times x squared is going to be x to the 5 halves, and square root of x plus 3 over x, that comes out to 3 over root x. If you want to convince yourself that that's true, remember that x to the 1/2, root x is x to the 1/2, and 3 over x is 3 times x to the negative 1, so that just comes out to 3x to the negative 1/2, like that. So that's how I got that. So what I want to do is let me rewrite this in the most useful sort of power form that will enable us to find the antiderivative. This is going to be the integral of x to the 5 halves plus 3x to the negative 1/2 dx. And now I'm not even going to bother to split this up with different integral signs. I'm just going to separately take the antiderivatives and add them together. So this comes out to x to the 5 halves over 5 halves. Oh, sorry, mistake there. I need to add 1 to that exponent. So x to the 5 halves plus 1 is x to the 7 halves over 7 halves and then plus 3 times the negative 1/2 plus 1 is 1/2, so that's going to be x to the 1/2 over 1/2. And I may want to simplify this a bit. That's going to be 2/7 x to the 7/2. And dividing by 1/2 is the same thing as multiplying by 2, so that's going to be 3 times 2 gives me 6. X to the 1/2 is root x. You can write that either as root x or x to the 1/2. It doesn't really matter. I'll write it that way. So that's the answer. So let's just do a few more antiderivative problems just to demonstrate these points. So let's do the indefinite integral of the cube root of x plus 7 over the square root of 1 minus x squared dx. Now recall that for this unit, we're really only finding antiderivatives of functions that you should recognize as the derivative of some other function. So first of all, or in the case of power rule functions. So here we can rewrite this as x to the 1/3 plus 7 times 1 over the square root of 1 minus x squared dx. For the power function, x to the 1/3, its antiderivative is going to be, I will add 1 to 1/3, giving me 4/3. And then that gets divided by 4/3. And then here we have 7 times the antiderivative of 1 over square root of 1 minus x squared. You should recognize from earlier units that 1 over 1 minus x squared is the derivative of arcsine. So since that's the derivative of arcsine, its antiderivative is just arcsine. So we're just going to rewrite this in slightly nicer form. 3/4 x to the 4/3 plus 7 arcsine of x plus c. And there we go. Okay, now let's do this problem. Let's do the indefinite integral of 1 over x root x plus cotangent squared x plus 1 dx. So we can rewrite this as indefinite integral of x times root x is x to the 3/2, so we have 1 over x to the 3/2, which is x to the negative 3/2. And the thing to recognize here is that cotangent squared x plus 1 is equal to cosecant squared x. That's one of the trig identities that we learned earlier. I realize some of you are looking at it and saying, well, am I really expected to remember that? The answer is yes, you are. So this is going to be, what we're going to do is add 1 to the negative 3/2, so that gives us x to the negative 1/2 over negative 1/2. And then the derivative of cosecant squared is negative cotangent. So just clean this up a little bit. That becomes negative 2x to the negative 1/2 minus cotangent x, which equals negative 2 over the square root of x minus cotangent x, and then of course the hardest part of the problem, the plus c, and we're done.